Hey, I want to talk about volume by rotation using the disk and washer method. So what we're going to do is we're going to calculate volumes of figures we create. So let's go to the theory here. Come on, buddy. There we go. So volumes from rotations. So the idea here is that we may have a graph on something similar to an XY plane like you see in the graph down here. And what we're going to do is we're going to take a region and we're going to rotate it around some line. And by doing that, we take that solid figure and create a three-dimensional object. So when we first started integration, one of the applications was that we could find the area under a curve. So in the two-dimensional space, we can find area, but when we wrap it around some line of rotation, then we create a three-dimensional object and we can find the volume. So I have two examples here. The one over here in the second graph, I think, is rotated around the y-axis and makes this kind of upside down bowl looking shape. I don't know what you would call the other one, but they're rotated around different axes. So just what we're trying to do here, that's your idea. Take some figure, rotate it to create a space. So the first thing we're going to talk about is the disk method. So the idea of the disk method is that when we were back in Cal 1 looking at adding up area, we talked about the height of the function all the way across here, and we made these infinitely thin little slivers. And the area was the height of the function, okay, f of x, times dx, which was the width. So the height times the width would give us an area. And the limits of limits of integration, the a and the b, the boundaries, the starting and stopping point, were what we were adding all these slivers up. Okay, so we had all these little slivers, we added them up, and that created an area. So the theory here is that we're going to take these little slivers and use them kind of like a radius. Okay, so the height of the function in some cases would be a radius. And we're going to take that radius and make a circle out of it. So if we make a circle here, that would be pi r squared, as you can see in the volume formula. So pi r squared. So taking that radius and taking it all the way around the circle creates a disk. And we could take a radius somewhere else, go around the circle, and make another disk. And likewise all the way across. So we have all these possibly different size disks all the way down the figure. So then when we take the A and B endpoints, it will add all those disks up. So we're creating disk by making circles, pi r squared, basically our function squared, and then we are integrating that over an interval to create a volume. So the fact that we do pi r squared creates an area, and then multiplying it by that extra dimension over a space creates the volume. Okay, so let's see this in action. Well, here are the formulas again. So we can look at this different ways. If we go around the x-axis or a horizontal line, we're going to integrate in terms of x. So the volume formula would be from endpoints A to B of pi r squared, which that would just be our function in some cases, r squared dx. So we want our functions to be in terms of x. So make sure you understand that if we're going around a horizontal or x-axis line. If we go around a y line or a vertical line, we're going to integrate in terms of y. So from A to B, pi times the radius squared dy, so everything's going to be in terms of y. So we're talking about the radius from the center of the rotation out. So that would be basically our radius. And that can be different in different functions. It just kind of depends on what we have and how we're going to rotate it. So up here in the around the x-axis, we got a bunch of circles laying on their, well, standing up, stacked together. added together, and around the y-axis we've got them stacked on top of each other. Okay. So let's see this in action, or at least try to see it in action. So here we have a figure, and it says find the volume by rotating around the x-axis. So let's see what that looks like. Around the x-axis would be here. So the figure is the line bound by x plus 2y equals 2. So if we go around the x-axis, we want to do things in terms of y. So we're going to integrate in terms of x. Okay, so go back to your formula. If we go around the x-axis, we want to integrate in terms of x. So our endpoints are going to be in terms of x. So the line that I have here in the first quadrant is x plus 2y equals 2. And they're showing us that we're going to run this thing from a all the way over at x equals 0 to b all the way over at x equals 2. So we're going to run it from 0 to 2. Okay? And we need to kind of manipulate this thing. So since we want it in terms of x, we need to get y by itself. So we're going to isolate y. So we're going to take the x plus 2y equals 2 and try and get the x on the other side and the y by itself. So I believe we get y equals 1 minus 1/2 x. Okay, so that is the radius from the center line of rotation, which in this case is the x-axis, all the way out to the function at different places. And when we rotate that thing, it's going to look more like a cone, because right now we have a wedge. But the formula will be pi times the radius squared, and we got the radius as 1 minus 1/2 x. So what we need to do is we need to square this thing. So from 0 to 2, I'm going to pull that pi out front of here. But let's go ahead and square this. So it's going to be a full. So 1, and it looks like it'll be minus x, because it'll be minus 1/2 x plus minus 1/2 x. And then it'll be plus 1/4 x squared dx. So now it's time to integrate. So 1 becomes x, negative x becomes negative 1/2 x squared, and then 1/4 x cubed becomes 1/12 x cubed. Now that'd be a plus c. There is a pi times all this, but it's going to run from 0 to 2. So that pi I pulled out front is just so I have a constant and not in the way. So we're going to let x equal 2 as we evaluate this thing. So we'll have pi, and I'm going to plug 2 in. So it'll be 2 minus 2 plus, that'll be 8 over 12. So that'll be 2/3. And then it'll be minus when we let x equal 0. And that'll be pi times 0 minus 0 plus 0. So all these cancel out. So it looks like in the end we get 2/3 pi. And that should be a volume. I don't know how much sense that makes. But basically it is a cone if we revolve it. If you think about taking this thing and revolving it around the axis, it creates a cone kind of like this. So if we lay it on its side, it's a cone that has a radius of 1 if we come out from the center of the base out, and a height of 2. And if we just want to track that, remember that the volume of a cone is 1/3, let's see, pi r squared h. Yes, so that would be 1/3 pi r squared would be 1 and h would be 2. So that comes out to 2/3 pi. So that's a figure when we create it that intuitively we could get the volume by itself. But if it's not a regular geometric figure that we know the formula for, it's not going to work out for us. Okay, let's do the same thing but a little bit different. Okay, so let me just say this was the x-axis and we rotated it around there. Okay, so let's take the same figure or the same region and rotate it around the y-axis. So this time we're going to go around the y-axis. So it'll still look like a cone. It'll just be oriented differently. Okay. So in this case, we want to run this thing through the y-axis. So that's going to have y endpoints of from the figure 0 to 1. And we're going to have pi r squared. Well, what's our radius in this case? Well, we want it in terms of y. So we're going to take the x plus 2y equals 2 and get x by itself. So x will be 2 minus 2y. Okay, so that's what we're going to square. That's our radius for that figure. Okay, so basically what we're doing is now we're doing disk this way, flat disk, because we're going around the y-axis. Okay, so in this case we still need to full. I'm going to pull the pi out front. So 4 minus 8y plus 4y squared. That's the squaring, the FOIL, but we still got to integrate. So pi out front would be 4y minus 4y squared plus 4/3 y cubed, and that'll be from 0 to 1. So when we let y equal 1, we get pi times 4 minus 4 plus 4/3. And then we're going to let y equal 0. And that'll give me pi times, let me clean that up a little bit. It was going really good there. Minus pi times 0 minus 0 plus 0. So all that goes away. So in the end, we end up with 4/3 pi, which is just a different shaped cone. Okay, so basically we've got these little discs stacked on top of each other, and we're adding them up. But because the orientation is different, it creates a different cone. This cone has we talked about it from the standpoint of a cone formula, 1/3 pi r squared h. In this case, the radius is 2 at the base and the height is 1. So the 2 gets squared, so when you plug that in, 1/3 pi times 4 times 1, so you can see very quickly that you do get something different. So it's a different dimension, so you get a different volume. All right, we're going to try some more in a moment.